My project is Risk-averse batch active inverse reward design, an approach related to AI alignment and technical AI safety. Preventing an AI catastrophe is a very pressing problem, as it is very important, even an existential threat. It is also very neglected relative to other problems. So, how is an AI trained? An agent acts upon an environment and makes a policy. This has the goal of maximizing the total rewards in a training environment, which are computed using a reward function, and this is what determines its behavior. But the behavior of the AI is different than the intended one, due to its training on a reward function in some training environments. This causes serious side effects. These factors cause two specific problems. Reward misspecification. The agent tries to achieve the goal in a different way than the intended one. And goal misgeneralization. Its learned policy cannot be adopted on new environments. My project aims to solve these problems by finding a reward function that best depicts the intended behavior, gaining information in real environments, and making decisions that are safe and certain. Now, let's talk about the existing approaches that are utilized in my project. But first, let's have a look at what the environment and the rewards are. We have the robot, which can move in 4 directions, some walls where it cannot move, and the start and goal states. The reward function, which is the same for all cells, is multiplied by the features apart in each cell, to give the reward for that cell. When the robot moves in the grid, its goal is to maximize the total rewards collected. Both described approaches try to find the true reward function, which depicts intended behavior. They compute for each possible reward function the probability that it is the true reward function. In inverse reward design, we are given a human-made reward function that has the intended behavior in a training environment. Then we compute the probabilities described before. Based on this, we also compute a policy that avoids risky actions. To compute that risk-averse policy, we take a sample of weights, chosen with the probabilities predicted before, and compute the reward of the state with each one of these weights. Then we compute a trajectory that takes big rewards, but also in which the rewards are more certain. Active inverse reward design, the main approach that I used in my project, is a process where we continuously update the desired probabilities by asking the human to choose which one of some given reward functions is better. This is done using a query, which is a set of n reward functions from all possible ones. For each query, the human chooses the function that he thinks best represents intended behavior. Now, let's move on to my project idea. Risk-averse batch AIRD is an improved version of the previous approach that consists of some batches with a specific number of environments, a probability distribution over the possible reward functions, the queries that were defined before, risk-averse planning, such that the actions the agent takes consider all the probable rewards. For each batch, we do the following steps. First, for a constant number of iterations, we find a query from which we can learn the most about the reward function and update the probabilities using its answer. Then we optimize a risk-averse policy that maximizes the mean reward over the possible functions, but penalizes the uncertainty we have about the reward in each state. Here is an overview diagram of the idea. We have the initial probabilities and the query, which is answered for each batch environment and improves these probabilities. We repeat that a number of times and move on to the next batch. After each batch, we also use the probabilities to make a risk-averse planner, which can safely be used in real-life scenarios. I evaluate the performance of my idea. After each batch, for each test environment, I compute the optimal reward of a planner that knows the true reward function, and the rewards of an unsafe and the risk-averse planner using the probabilities found. Then I measure the difference in performance of the optimal planner with the unsafe one, with the test regret, and the risk-averse one, with the risk-averse regret. I also record the variance of both planners based on the reward function samples, and plotted their trajectories. Let's see the results now. First of all, in the x-axis I have the number of inferences, with the number of answers the human needs to give in total. In the initial AIRD paper, using the same query choosing methods I did, the performance approached optimal after about 50 queries. However, using my approach, the total number of inferences is lower, to about 30 queries. It almost achieves optimal performance, and we can make the number of queries even lower by increasing the number of environments in each batch. When we are still uncertain about the intended reward function, risk-averse performance is worse than the unsafe one, but risk-averse planner constantly makes more certain choices. Also, both performances become optimal at the same time, which when the true reward function is found. Here's a comparison of the trajectories of the risk-averse planner and the unsafe one. The red color means high uncertainty, and the blue color big reward. We see that the risk-averse planner chooses a trajectory that is safer than the one of the optimal one, while still reaching a goal and collecting as many rewards as possible. In an experiment where I added new features in each batch, the number of inferences was about the same as before, showing its ability to adapt quickly to unknown scenarios. Also, the variance of the risk-averse planner was shown to be significantly lower than the unsafe one, noting its importance on new environments. AIRD didn't have that capability, since it was only trained on one environment. How can my idea have an impact? My project achieves more certain actions, less human intervention, and fast recovered optimal performance. It also continuously adapts to new data and learns from a behavior, not a simple reward function. This leads to lower chance of unexpected actions, smaller negative incentives for businesses to adopt this model, adaptation in real-life scenarios, and approaching the behavior humans want it to. In the long term, we will have less of a risk of turning against humans or seeking power, and will reduce the existential threat of AI. What I will do after the fellowship for my idea to have a bigger impact. I will make improvements to the algorithm for increased efficiency and usability, write a research paper on the approach and present it in a related conference, adapt the process to real-life systems, like household cleaning robots, to not cause damage when being in a new environment, follow a career related to AI alignment, and apply the knowledge I gained to improving other subsectors of it. Here are some references to related work, as well as the papers used for my approach. This was my idea, I hope you liked it.